Hi everyone, welcome back to another GCSE Physics session. Today's session is going to be on gas pressure and volume. So yesterday we looked at gas pressure and temperature, and now we're going to see how it varies with volume. As always, this session is 1 hour and will be recorded and uploaded onto YouTube later. So if you have missed anything or you want a refresher on something, then you can just go and look at that. If you don't know me already, my name's Preshayla. I study physics at Loughborough University and it's my 4th year as a tutor. And what we're going to cover today is being able to define gas pressure in terms of volume and understand how the two are linked, understand work done and how it leads to pressure, and pressure and volume through experiment, and then finally explaining why pressure varies with volume. So there's not really that much content to go through today. It's a small topic of molecules and matter. So we've got lots and lots of time for exam practice today and all your questions on the topic that we've just covered. If you do have any questions throughout the session, put them on the chat and I will try to get to them as quickly as I can. But we will be having our Q&A session at the end anyway. Cool. So let's start with a summary of yesterday's webinar as usual. So we talked about internal energy and how increasing the temperature of a substance affects its internal energy. So that was by saying increasing the temperature makes the particles move faster, increases their kinetic energy, and increases their internal energy. So internal energy is, again, this idea of combining two different energies together, okay? So internal energy is the internal energy of the molecules, which is made up of two parts. The first part is the kinetic energy, which relates to the motion of the molecules. And the second part is potential energy, which relates to the position of the molecules. Then we talked about an increase in internal energy. So increasing internal energy can lead to one of two things. It can lead to a change in temperature or a change in state. A change in temperature uses E equals mc delta theta, that equation, and a change in state uses our new equation, latent heat. Now, again, two types of latent heat. Latent heat of fusion, so that's going from a solid to a liquid. Latent heat of vaporization, which is going from a liquid to a gas. So in an exam question, it's important that we notice which one they're talking about. However, there are not that many exam questions to do with latent heat. Comparing particles in solids, liquids and gases, so building on from our kinetic theory of matter, thinking about how molecules and particles are placed, how they relate to one another, what their forces are between them, and so on and so forth. And then we talked about gas pressure and temperature. So how are the two related? Well, if we increase the temperature, that increases the kinetic energy. Okay, so temperature, kinetic energy increases speed, more collisions, more force, more pressure. Okay, and then we talked about P equals F over A briefly to remind us of the equation for pressure. Finally, we looked at observing random motion. So how can we tell that a gas moves completely randomly? So we looked at a mini experiment, which is putting some smoke into a glass kind of container, shining light through that container and looking at it through a microscope and seeing that the smoke constantly moves in random directions. The reason that we can see it is because the smoke particles are much bigger than the gas particles. Okay, so that was yesterday's webinar. So now let's talk about volume and pressure. So we know that a volume of a gas depends on both its temperature and its pressure. Okay, so the volume of a gas depends on its pressure and its temperature. A gas can be compressed or expanded by pressure changes. So we can compress a gas and increase the pressure or expand a gas and decrease the pressure. In other words, we can decrease the volume, which means compression, and increase the pressure, or we can increase the volume, expand it, and decrease the pressure. Okay, because the particles have more space to move, so they're less likely to collide with each other. There are less collisions, which means less force and less pressure. So pressure produces a force. We know this. When we have collisions against the walls of the container, it produces a force. Now, what we haven't talked about is that that force that is created because of the collisions is at right angles to the wall. So if I draw a little diagram, this is our container and it's got our gas in it. I'll draw a particle of a gas and a particle of a gas and a particle of gas that is about to hit the wall. Now, when it hits the wall, the force comes off this way. Okay, so the force is at right angles to the wall of the container of the gas. Now, in an exam question, how could they test this? Well, they might give you a diagram of a beaker like I've done with gas particles in and ask you to show the direction of the force, of the net force in the container. Okay, so it's all about these gas particles colliding with the walls of the container. Okay, so colliding with the walls of the container. And that is what creates our force. Those collisions create our force. And that force, by P equals F over A, creates our pressure. So remember, P equals F over A. If we have a bigger force, we have a bigger pressure. So how does this relate to volume? We use this again in mini experiment to help us understand. So here you can see that we have a beaker, just a simple glass beaker, which is filled with a gas. And then we have this sort of plate and it's attached to a kind of stick which we can push down like a plunger. And this is known as a piston. Okay, so we can push this piston down, as you can see in the diagram, and compress, okay, key term, compress the air in the beaker or the tube. Okay, so when the piston is pushed into the tube, the volume of the air decreases. Okay, we can see that we've gone from a bigger volume to a smaller volume. And that is because we've compressed it, compressed the air. And you can see that the particles are now much closer together. They're much more compressed. So because they are more compressed, there is less space for them to move around, which means there's going to be more collisions with the walls. And because there's more collisions with the walls, there's more force. And because there's more force, there's more pressure. Okay, so you can see that on our pressure gauge, which is this dial here, the pressure has gone from almost zero to almost maximum because we have compressed the volume. So we can see now that a decrease in volume leads to a decrease in, an increase in pressure. Okay, so by compressing our gas, we increase the pressure. Now, there is one consideration that we need to make when we do this experiment. We must do it slowly. Okay, we must do this experiment slowly. And the reason for this is, if we do it fast, the temperature will change. And that's going to affect our readings because we know temperature also has an effect on pressure. Okay, so we don't want our temperature to be changing if we're changing the volume. We only want to be changing one thing at a time. We either change volume or we change temperature, not both at the same time. That doesn't work. Okay, so if we are going to be changing volume, we want to keep our temperature constant. So the temperature of the air in the tube does not change, but we can only make sure that this is the case if we do it slowly. So I'll just write that down for us as well. If we are changing pressure, volume, then we should not be changing temperature. We should only change one variable. Okay, so we only have one independent variable. Remember, independent is the variable that we change. Okay, that's the same in any experiment that we've done in our GCSEs. We only ever have one independent variable. Everything else is control variables. So in this mini experiment, our control variable would be temperature, but our independent variable would be volume. Volume is the thing that we're changing. If we're changing volume, everything else must stay the same. The dependent variable, the thing that is changing because of the change that we're doing, is pressure. It's the thing we're measuring. Okay, so let's talk about why this happens. So why do we get more force? Why do we get more pressure? So work is done as force is applied to the piston. Now I'm just going to remind you of what work done means. Work done is a force that works to create motion. Okay, so work done happens when a force works to create motion. So in our case, our force, us pushing down on the piston, creates motion. We're pushing, the piston moves. It's as simple as that. That's all work done means, is a force working to create motion. Okay. So we're applying work done as we apply force with our hand by pushing down the piston. Now this applied force that we're putting in has to overcome the force produced by the pressure of the gas. Okay, so our force that we're putting in has to be bigger than the force that is created by the pressure of the gas. So let's draw that in diagram version to make sure that we really understand. So we've got our beaker of gas, and we've got our piston in here, which we're going to be pushing down on. Okay, so we're pushing down on that piston, and what is important is the force that we're applying on the piston is bigger than the force that our gas particles create, which remember is at right angles to the container. If that is not the case, nothing's going to happen. We're not going to decrease the volume, we're not going to increase the pressure. Now, again, if this compression does not happen slowly, the work done on the gas increases its internal energy and its temperature. So let's take that statement and think about it. If we don't do this compression slowly, if we don't put our force in, if we don't do our work done slowly, then it's going to increase the internal energy. So by applying a quick force, strongly and fast, our internal energy store is going to increase. Okay, it's going to increase our kinetic energy and increase the temperature, which we do not want. Remember, we're only changing volume, not temperature. So we must do it slowly. Okay, so we know we're doing it slowly, and by compressing the gas slowly, the gas loses energy by heating its surroundings at the same rate that the energy is transferred into it. So yes, there will still be some energy pumped into the gas, but it's losing energy as well. So the overall energies cancel out and there is no heating. Okay, so energy that we're transferring into it is going to be some. Okay, inevitably there is going to be some energy because we're putting some kinetic energy in, and that kinetic energy needs somewhere to go. But the energy that we're transferring in is happening at the same rate that the container is losing energy by heat to its surroundings. So it all cancels out and we're fine. We don't get any heating if we do it slowly. If we do it fast, it doesn't have the chance to lose its heat to its surroundings. And therefore, we have no change in internal energy and no change in temperature. Okay, so internal energy is completely proportional to temperature. Okay, so we have another mini experiment here. And what this is talking about is how does volume change with pressure, or how does pressure change with volume? So we can see that as we increase the volume of our oil, our pressure goes down. Okay, so we might start with 20, and then we increase the volume and our pressure decreases. Okay, now the oil is there not as a thing that we're measuring. Okay, it seems weird, but actually the oil is there as a filler. All we care about is the gas in the tube. Okay, so we've got a glass tube here, and you've got some gas in the tube and you've got some oil, but the oil is only there so that we can measure the gas. Yeah, so we can see how much gas is in there. So by increasing the amount of oil, if we get this oil to go up more, we decrease the amount of gas, right? You can see that if the oil starts to fill up the container more, we don't have as much space for the gas. So if we increase the oil, we decrease the gas. And if we decrease the gas, we're decreasing the volume of the gas. If we decrease volume, we increase pressure. Okay, so you can see that we're decreasing volume and increasing pressure. Okay, so oil is not the thing that we're measuring the volume of or the pressure of. We don't care. The oil is just there as a filler. It's just a nice way of being able to see how much gas we have. What we care about is how much gas is in our container, which is why the scale starts from 0 at the top, which is weird. But it starts from 0 at the top because the gas is going to fill the top. And so it just makes it much easier to measure the volume of the gas. Okay, so this person has varied the volume and measured the pressure. So volume is an independent variable and pressure is a dependent. So volume, pressure. So volume is the independent and pressure is the dependent. Okay, so control then would be obviously temperature, the oil, density of the oil. I'm sure you can come up with loads of controls. Okay, so they've increased the volume, decreased the volume of the gas. They've decreased the volume of the gas just by increasing the volume of the oil. Now, because they've decreased the volume of the gas, they've increased the volume, increased the pressure. But what is really special about this experiment is when they times pressure by volume, they get the same thing every time. Okay, so you can see if they do 100 times 36, they get 3,600. And the same with the next reading, and the same with the next reading. So by this experiment, we can now tell that pressure times volume is constant. Okay, which brings us on to a new equation. PV equals constant. Now that constant could be anything, but it's the same always for that gas. So the pressure of the gas times the volume of the gas is always the same. Okay, and if we are going to decrease volume, like we've done in this experiment, then we increase pressure. So you can see that they're always going to balance out. Okay, so that is how we approach the investigation of pressure and volume. Not a required practical, just a nice mini experiment to help us understand the variation of pressure against volume. Okay, so let's go more into depth about why we have this variation. Why does pressure change with volume? So what is important to remember is that in this experiment, we have control variables. We've already talked about the temperature being a control, but also the mass is a control. Okay, so these are our controls in our little experiment. Okay, so by keeping the mass constant, we can keep the same number of molecules. So that makes it a fair test. Keep the same number of molecules so that we can really tell whether the pressure is getting higher. Same number of molecules and constant temperature throughout the experiment. Temperature should not change throughout the experiment. Therefore, we would have a constant speed. Now, the reason that a constant speed is really important is because if we have a constant speed of the molecules, we know that they should be doing the correct amount of collisions. So by keeping mass and temperature the same, we now have a fair test. We have a good set of control variables and we can properly understand what is happening with pressure and volume. Control variables are taken care of, so now we can do the real measurements. So if volume of the gas decreases, pressure increases, so it's this opposite relationship. Why does this happen? Well, when we decrease the volume of the gas, there is less space, right? There's less space for that gas to move around. And if there's less space for the gas to move around, the molecules travel less between each impact. Okay, so they've not got as much space to kind of move around, be free. They're really kind of constricted. And so they have less space to move around. They're just in a less amount of space. And because they've got less space to move around, they're going to constantly collide with the walls. Yeah, they're going to constantly collide with the walls. And if they constantly collide with the walls, we've got more collisions. And more collisions means that the impacts per second increases. So the collisions per second increase. And if that happens, total force per area increases. So the total force in the area of that container increases. Therefore, we have a higher pressure. So it goes from less space, less collisions. Oh, sorry. Beg your pardon. Less space, more collisions, and more force. So more pressure. Okay, so space, collisions, force, pressure. Just like yesterday, we had temperature, kinetic energy, speed, collisions, pressure. I like to think of them as these kind of flowcharts of words. Yeah, so starts off by less space. That is exactly what we're doing. We're giving it less space. More collisions, more force, more pressure. So it's this chain reaction kind of flow chart. That's how I like to remember it. And the same with what we did yesterday, the variation of pressure with temperature. So we talked about increasing the temperature, increases the energy, increases speed, increases collisions, increases the pressure. So these little flowcharts of words to help us describe the process of what happens when we change volume or temperature to the pressure. Okay. So as we mentioned earlier, we have this new equation. P times V is constant, or it can also be written as P1V1 equals P2V2. Now let's talk about the second form of that equation. What that means is where we have a 1, that means our first kind of reading, yeah, our initial readings. Then we might do the experiment again at some other pressure, which matches some other volume. And that's our second set of readings. Or it might be our final set of readings. So any two sets of readings, when you times them together, should be the same thing, roughly. It's not always going to be exact. Okay, so any two sets of readings could be initial, could be second and final. It's just your first reading and your second reading that when you times them together, give a constant. Okay. So we know that if one thing increases, the other decreases. This is called an inversely proportional relationship. Okay, an inversely proportional relationship. And we can show it on a graph, and it looks something like this. Inversely proportional relationship. Inversely proportional relationships are important when we talk about different equations in physics. So inversely proportional relationships are when one thing goes up. I'm going to say this in really simple terms so that we understand it, but make it more formal in your exam. You wouldn't write this. Or when one thing goes up, the other thing goes down. Okay, so more formally, an inversely proportional relationship is when one thing might double, the other thing might half. Yeah, so yes, one thing goes up, one thing goes down, but it's more mathematical than that. One thing doubles, the other thing halves. Okay, so we can actually see that in our diagram. If one variable doubles, the other halves. So not only does it go up and down, it does it mathematically. So doubles, halves. And it's the same thing for if one thing triples, the other is divided by 3. Okay, and so on and so forth for any number. If one thing is times by 100, the other thing is divided by 100. And that's how it works. And we can see that in our graph. If we double the volume from 40, to 80, we see that the pressure goes from 80 to 40. So if we double the volume, the pressure halves. if we double the pressure, if we go from 40 to 80, the volume halves. Okay, so it's this idea of one thing going up, the other thing going down. And more mathematically, one thing doubling, the other halving, or one thing tripling, the other dividing by 3, or whatever it happens to be. So let's have a go at attempting a question. So for this question, you've been given 2 sets of readings. So this is our first set. In a chemistry experiment, 0.00020 meters cubed of gas was collected in a flask at a pressure of 125 kilopascals. Pressure is measured in pascals. Calculate the volume of this mass of gas at a pressure at 100 kilopascals at the same temperature. Very wordy question, but what this basically boils down to is Boyle's law, which is P1V1 equals P2V2. So we're going to be using this new equation in this question. We've already been given V1 and P1, and we've been given P2. So we need to find V2. So remember, P1 we've been given, V1 we've been given. That's our initial reading. But it wants it now at a different pressure. Notice that in the question, they've said the same temperature and the same mass. Remember, there are control variables. They must stay the same. So let's have a go. What do we think V2 would be? So first of all, let's rearrange our equation. So we're trying to find V2. Calculate the volume. Yeah, the volume, the new volume at the new pressure. We're trying to find V2. So let's rearrange for V2. Well, that's P1, V1, divided by P2 equals V2. Okay, so I'll just draw it out for you guys as well. So P1, V1, divided by P2 equals V2. So have a go. What do you think V2 would be? What do you think V2 would be? We've rearranged our equation for V2, which is what we're trying to find. And we've been given P1, 125, V1, 0.0002, and P2, 100. So notice that P1 was our initial reading value and P2 was our secondary reading, yeah, our new reading, however you want to think of it. Initial, new, initial, final, first, second. It's just 2 sets of readings which we can compare. So also notice that we have K here, kilo. So we must times our value by 1,000 to get it into pascals. So you need to go from kilopascals to normal pascals. So make sure that you do that before you do your division. And the same with 100, that needs to go into pascals. We can't be doing our equations with any kilos in. It has to just be the normal unit, pascals. So I'll give you 30 seconds to have a go at that. Some of you are already getting the correct answer, which is great. So make sure that you convert into the correct units. Now you can use 0.0002 meters cubed, or you can use 200 centimeters cubed. but the correct unit that it should be in is meters cubed. So they've already given you the conversion. Yeah. So personally, I would use meters cubed. There's no point using 200 centimeters cubed because you're just going to have to convert it. And they've already done that for you. Yeah, so we want to be using meters cubed and pascals, not centimeters cubed, not kilopascals, the normal basic units, meters cubed and pascals. Okay, so let's go through it. We have P1 is 125 kilopascals. So 125 kilopascals will be times by 1,000. So 125,000. Times by our volume, which has already been given to us in meters cubed nicely, 0.00020. And we divide it by P2, which is 100,000. Okay, so when we do this division, we should be getting 0.00025. 0.00025. Okay, so a new pressure, a new volume of 0.0025. Okay, so that's how to do a pressure volume constant question. Okay, so let's stop with the content. That's all the content that we have for today, and go on to our quiz. So same drill as always. There are 15 questions today. So we finished all the content for molecules and matter. So let's have a nice wrap-up quiz to consolidate everything that we've learned. Don't worry if you get some wrong, we'll be going through the answers at the end and consolidating even further with some exam questions. So if you haven't done one of these quizzes before, you want to be writing joinmyquiz.com into your web address, browser or whatever, just type it in and then type in your game code. So 907346. And I will put the link on the chat as well. Someone said, what would happen if you changed the temperature and the volume? If you changed both, then you're just not going to get the pressure that you're looking for. Okay, you're not going to get that proper pressure relationship. It's not kind of a fair test. We never have two kind of independent variables, so. Someone said, what does the A stand for in the equation? P equals F over A. That's area, surface area. Do these style questions come up in AQA? Absolutely, and we're going to be seeing some more of them later on. Does the force in the container exert a force on the piston? Yes. So Newton's third law says that every action has an equal and opposite reaction. So the force on the container exerts a force on the piston. Is this a required practical? No. What can a constant do? A constant can't do anything. It's just a number that is always the same. Okay, it's not really got any physical properties. It's not got any relevance. It's just that it's always going to be the same. What's GPE? GPE is gravitational potential energy. This is a different form of energy which happens when an object has the potential to fall. And if you want to know more about GPE, then we did a webinar on it in the energy section. So if you just type in energy stores, I think it is, into the My Tutor channel, then you'll be able to find that webinar and go into depth about all the different types of energies. Okay, so there's 20 out of 36 of us on so far. I'll give us 2 minutes before we start. While we're waiting, if you have any questions about general kind of physics, general kind of exam practice, how you should approach exam questions, any general questions, that's absolutely fine as well. I'm happy to answer those. Yeah, so it doesn't just have to be about content, it can be about exam style and practice as well. Or advice on how to revise, advice on hard topics, anything like that. Okay, so if you're not in already, the website that you need to go to is joinmyquiz.com and the game code is 907346. If you can't do that, then the link is on the chat. You can join from a computer or a smartphone. And yeah, if you missed it, there are going to be 15 questions. They all have a 30-second kind of timer, and they're all multiple choice. Okay, so let's start. Okay, really good, guys. We've got 70% accuracy. Just try and keep it there. Okay, looks like lots of us are getting to the end, so I'll give us 1 more minute to complete the questions. Okay, cool. Looks like loads of you are done now, so let's finish up. We got a final 74% accuracy, which is good. Okay, so the first one, when a warm object is brought near a cold object, the cold object will warm up. Yeah, so if we bring just a cold object, so for example, you know, even if we're coming in from the cold, we put our hands on the radiator, our cold hands will warm up. Which of the following is not a change from liquid to gas? So when we're going from liquid to gas, it can be called vaporization, boiling, or evaporation. But gas to liquid is condensation. Okay, so liquid to gas, vaporization, boiling, evaporation. The other way around is condensation. A gas partially, most of the time, sometimes or completely fills its container. A gas completely fills its container. Okay, it can flow, it can fill its container. The physical state of a type of matter depends mostly on how what are arranged and how they move. So that would be its atoms and molecules. The structure of the molecules will tell you whether it's a solid, liquid, or a gas. Different objects don't heat at the same rate because they have different specific heats, energy, boiling points, or temperatures. Now, I've highlighted rate because it can be kind of confusing, this question. Different objects don't heat at the same rate because they have different specific heats. Yeah, so specific heat tells us how much energy is needed to raise the temperature of that material. The boiling point just tells us what temperature, yeah, not the rate at which it warms, just at what temperature does it boil. Okay. The energy of moving particles is called kinetic energy. So we know that kinetic energy just means the energy associated with movement. When the attractive forces holding particles together are strong enough to hold them together as a group, but not in a fixed position, they form a liquid. Okay, so you can hold them together slightly, but not in fixed positions. Fixed positions would mean it's a solid. So this would be a liquid. The what remains constant when a liquid reaches its boiling point. All of you got this right, which is the temperature. So the temperature remains constant when a liquid reaches its boiling point. The higher the temperature, the particles move. The higher the temperature, the faster the particles are moving. If the attractions between particles are strong enough to hold the particles in almost fixed positions, the matter is in a what state? That's again liquid. Because particles in a liquid move more freely than those in a solid, liquids have no definite shape. When a substance is heated, it gains internal energy. Pressure produces a net force at right angles to the wall of the container of the gas. So remember, that was when I drew the diagram of the container, particles in it, and the force that I drew was going to the container, outside of the container of the gas. If the volume of a gas increases, the pressure decreases. It's that opposite relationship. And Boyle's law is PV equals constant, or P1 V1 equals P2 V2. Okay, so you would have had to tick both to get the correct answer, but remember that either version of the equation can be used depending on what the question kind of asks for. Okay, so that's the end of our quiz. Well done, everyone. We ended up getting 77% accuracy, which I think is our best one yet, so that's really great. Let's go back and do some more exam questions. Okay, so here we have a question talking about kinetic theory. So according to kinetic theory, all matter is made up of small particles, and the particles are constantly moving. So these are the particles in a solid, and they've said that 1 kilogram of gas has a much larger volume than 1 kilogram of solid. Why is that the case? So have a think about why 1 kilogram of mass would have a much larger volume than 1 kilogram of a solid. Have a think. So what do we think might be the reason for this being the case? So kinetic theory is talking about how the particles are arranged and what the forces are between them. So 1 kilogram of gas would have a much larger volume simply because the particles are much more spread out. Okay, so the density of a gas would be much kind of lower than the density of the solid. And we can use our equation: density equals mass over volume to help us understand. So we have the same mass, but we have different densities, and therefore we have different volumes. Now, one thing that I want to point out to you guys is that when looking for past paper questions, when I was looking for my exam questions, the one that came up the most, like literally every single past paper, is specific heat capacity. Okay, so if we remember, specific heat capacity is E equals mc delta theta, or change in temperature. Okay, so that comes up the single most. So we need to be really confident on how to do those. Remember, C is a specific heat capacity, which in this case is 4,200. Change in temperature is 8 degrees, and you've been given the energy, so we need to find the mass. But yeah, really, really common exam question that you guys can attempt at home. This tends to come up less. This is pressure, force, and area. So you'd have to find the area of the tank and work that out. So, and then do the pressure equals force over area equation. These ones are taken from EdXL just because there weren't so many for AQA, and AQA literally tended to be a specific heat capacity over and over again. This one is talking about liquids and densities, so it tends to be less about kind of the arrangement of the particles and more about the density. Okay, so they put a big emphasis on density and on specific heat capacity. Like I said, there's hardly any questions on latent heat. Yeah, so hardly any questions on using that new equation that we talked about, which was Q equals ml. It's still important for you to know, but yeah, less questions that come up. Okay, so I've put a few questions up while I've been talking for you guys to attempt at home. Try to do the specific heat capacity ones first, but yeah, as I said, this will be up on YouTube, so do go and have a go at these questions in your own time, and you can find all of them on Physics and Maths Tutor anyway. So just pause the video when you watch it back. I think that's all from me in terms of questions and content. So yeah.
Thanks, Preshayla. Thanks everyone for attending this morning. We have English, Maths and Chemistry the rest of today. If not, see you next week for our next physics session. I hope you found this lesson really valuable. And as Preshayla said, later today this should be uploaded to YouTube. So if you wanted to check out any of the slides again or answer any of the questions at the end, then just head over to YouTube later today and you'll be able to do so. But hopefully see everyone in another session soon. Bye.
Bye.